This is Math 30-1, and we are in Chapter 5, which is looking at exponential and logarithmic functions. In our previous lesson, we were introduced to logarithmic functions, and today we're going to go a little bit further as we examine logarithms and look at some laws of logarithms that correspond to the exponent laws that we learned in earlier grades. So to begin with, here you see two warm-up questions that I would like you to do without using a calculator. And then we'll see that this will be an illustration of the first law of logarithms. So you can pause the video now and then restart once you've finished these two questions. All right, for question number 1, here's what I did. I rewrote the 32 as a 2 to the exponent 5 and the 8 as a 2 to the exponent 3. So I can multiply these two powers with the same base. When I do that, I can add their exponents. Now you'll recall that if I have a log base 2, this logarithm is saying if I was to rewrite this number as a power base 2, the logarithm gives me the exponent. Well, 2 to the 8th is already a power base 2, and so the value of this logarithm is the value of this exponent, and there's the result that we get. Question number 2 is similar in that it has a log base 2 and it has the 32 and the 8, but here we're adding. But as you hopefully discovered, as we evaluate these two logarithms, again writing the 32 as a 2 to the 5th, so log base 2 of 2 to the 5th is equal to the exponent of 5, and log base 2 of 2 cubed is equal to the exponent of 3, add the exponents, and we get the value of 8. So what we're observing here is that this logarithm expression that we have in number 1 and this logarithmic expression that we have in number 2 are identical. So in general, if we're taking the logarithm of a product, so you'll remember that what we've said previously is that a logarithm operates on a power. So this m and this n we're thinking of as being powers, and the logarithm is imagining them to be powers base b. So if these two powers have the same base, when I multiply the powers, I can add the exponents. Well, remember, a logarithm is an exponent, or gives an exponent as output. So this is equal to log base b of m plus the log base b of n. So on the right-hand side, we are adding exponents. If we think of the exponent laws, when do we add exponents? It is when we were multiplying powers with the same base. So that's our first law of logarithms. And here we'll do a proof to illustrate that this is always true. And the way we'll begin this proof is by doing a bit of a substitution. So we're going to imagine that this uppercase m is equal to, we could rewrite it as b to the exponent lowercase m. And the uppercase n, we can rewrite as a power base b, where the exponent would be that lowercase n. So here we have the left side of the identity that we wrote above, log base b of m times n. Now, given this description that we put up here, these substitutions that we can make, we will just replace the uppercase m with a lowercase b to the m, and the uppercase n with a lowercase or b to lowercase n, because we've defined this uppercase m to be this red part and the uppercase n to be this lowercase b to the n. Well, here, because we're multiplying powers with the same base, that means we can add the exponents. So we get the next step in our proof. And we know that when we're working with logarithms, if this base and that base are identical, the logarithm just tells me the value of the exponent, which in this case is the sum m plus n. Now here we need to take a bit of a detour. So up here I looked at this left side of this let part. And if this is true, then I can rewrite both of these expressions in logarithmic form. So remember, if I have this exponential equation, uppercase m equals b to the lowercase m, then the exponent is m. So here I have that exponent of m, and that's equal to log base b of uppercase m. So that's how we switched from exponential form into logarithmic form in our previous lesson. So we know that those two equations are identical. They're describing the same relationship. And it's the same thing with the uppercase n equaling b to the n, where our lowercase n will equal log base b of uppercase n. That sets us up for our final substitution, which is to say that this lowercase m is equal to log base b of uppercase m, lowercase n is log base b of uppercase n, and we've proven the identity. Let's continue on and look at some examples. Well, these examples are actually going to set us up for our next laws of logarithms. So I'm going to do these two questions similar to how we did the first two warm-up questions. So I'm going to rewrite, since I have a log base 2, I want to rewrite the 32 as a 2 to the 5th and the 8 as a 2 cubed. Since I'm dividing powers, I can subtract their exponents as long as the base is the same. So this gives me log base 2 of 2 to the exponent 2. And again, since I have a log base 2 of a power base 2, the logarithm is equal to the exponent, which is 2. Let's look at number 4. I have log base 2, 32 is 2 to the 5th, and log base 2, 8 is 2 cubed. And again, as we did in the previous question, since this base and that base are the same, the value of the first logarithm is 5. The value of the second logarithm is 3. 5 minus 3 equals 2. And again, I get these two expressions from number 3 and 4 equal to each other. So again, when I'm dividing powers, a logarithm operates on powers, it is equivalent to when I'm subtracting the exponents when I have the same base. And again, the logarithm is an exponent. Next example. Here I have an 8 multiplied to a logarithm. But again, I can rewrite that log base 2 of 32 as a log base 2 of 2 to the 5th. And the 8 is multiplied in front. And as we saw in previous questions, log base 2 of 2 to the 5th is equal to 5. So I get 8 times 5, which is 40. As I look at number 6, notice the similarity in that I have log base 2 of 32, but now I have an 8 in the exponent, whereas in number 5, the 8 was being multiplied. Here again, I can rewrite that 32 is 2 to the 5th, all to the exponent 8. Power raised to an exponent, I multiply those exponents to get 40 as the exponent. And again, since I have a logarithm base 2 of a power base 2, the value of the logarithm is the value of the exponent. So here what we see illustrated is that, remember, a logarithm in number 5, this logarithm is an exponent. So when I do this exponent times the 8, I have to imagine that I'm multiplying exponents. When do I multiply exponents? Well, that happens when I have this power raised to an exponent. That's when I multiply the exponents. And so you can see how this law is going to correspond to that exponent law. And here we have them summarized. And we won't bother proving these two. We'll just say, oh, trust me, these relationships can be proven similar to how we did the previous. So if I'm doing the logarithm of a quotient, that means that I can subtract the two logarithms. Now there's a danger here in the words that you repeat to yourself in your head. We can't say that dividing is the same as subtracting because it's not. They're different operations. But here I'm dividing powers inside my logarithm. When can I, or what do I do if I'm dividing powers, base b? That means I subtract the exponents, and each logarithm is an exponent. Similarly here, if I have the logarithm of a power, again, think of the m as a power, raised to the exponent n, power raised to an exponent, I can multiply the exponents, and log base b of m is an exponent. So is this n an exponent, as we saw on the left side. So let's use these in a few examples. So here I have log base 4 of 32 minus log base 4 of 2. Now, writing 32 as a power base 4 isn't easy, nor is it easy to write 2 as a power base 4. It can be done, but instead we can use this logarithm law up here that we have in blue and say, oh, since I'm subtracting these two logarithms, I can rewrite it as the logarithm of a quotient. So I can rewrite this as the log base 4 of 32 divided by 2. I can simplify the 32 divided by 2 to give me a 16, and that 16 I can more easily write as a power base 4. So it gives me log base 4 of 4 squared. And again, remember, this logarithm here says if I was to rewrite this 16 as a power base 4, what would the exponent be? The logarithm tells me the exponent is a 2. And there we have a goofy looking arrow, but our answer for number 7. Question number 8. We want to express this as a single logarithm. Now, just like with order of operations, we need to think about combining kind of the order that we're going to combine and simplify things here. So because I have this product here with the 2 times log y, and here a product of 4 times log z, I need to do this multiplication. I need to simplify that part first. So I'm just going to leave the log of x, and notice there's no base given, which means it's a common logarithm, a log base 10. The law of logarithms, third one that we looked at above, up here said if I have a logarithm of a power raised to an exponent, I can multiply that exponent in front. So I can do the opposite as well. I could take this n and write it into the exponent of the m. So that's what I'll do here. I will take the 2 and write it as an exponent inside the logarithm. So I have the log of y squared. And I have the log of z to the 4th. Now that each logarithm has a coefficient of 1, I can use those laws of logarithms. Now I can do it in small stages, and let me do that to begin with. So let's start by combining these two together first. Here I'm adding logarithms. A logarithm is an exponent. When do I add exponents? When I was multiplying the powers. So this is the same as the log of x times y squared. Now I have two logarithms being subtracted. A logarithm is an exponent. When do I subtract exponents? When I'm dividing the powers. So this is equal to the log of xy squared divided by z to the 4th. So notice that the logarithm that's being subtracted, this z to the 4th ends up in the denominator. Now we could have done this all in one step. So as long as we look here, since I have addition in front of this logarithm, here this is a positive invisible in front of this logarithm, that tells me that the x and the y squared will be in the numerator. Because I have a negative in front of this logarithm, that tells me that the z to the fourth will be in the denominator, and we could have skipped this middle step and just jumped right down to get to our final answer here. Now, that's not the only way we could have done this question. So let me look at another possibility. I'm going to start again by rewriting this as the log of x plus the log of y squared. But now suppose I was to take this minus 4 and take the negative into the exponent along with the 4. That would turn this into addition of the log of z to the negative 4. And you'll see as we go through this that we're going to get an identical answer. Now I'm adding 3 logarithms together, which means I can multiply the powers, so the x times the y squared times the z to the negative 4. And as you recall, this z to the negative 4 I could rewrite with a positive exponent if I took that z into the denominator and wrote it as z to the exponent positive 4. So we do get an equivalent answer. And there's question 8. Question 9, we want to write this as well as a single logarithm. But this time we have a bit of a challenge where we have a 3 here, but there's no logarithm with it. So I'm not actually subtracting logarithms. But what I'm going to do is I'm going to imagine that that 3 that's being subtracted actually is being multiplied to some logarithm. So I want to imagine that inside this bracket here, I have some logarithm, base 2 of something, that's equal to 1. Well, what would this question mark have to be in order for this logarithm to equal 1? Again, a logarithm says if I was to take this question mark and rewrite it as a power base 2, what it gives me is the exponent. So it's telling me that I could rewrite that 1 as a log base 2 of 2. Because this log base 2 of 2 has an invisible exponent of 1, so what is this logarithm equal to? It's equal to 1. So I've introduced a logarithmic expression that is equivalent to 1, and so that rule that we have known for many, many years, that we can multiply an expression or a number by 1 in whatever disguise 1 shows up, and we still get an equivalent statement. So here, log base 2 of 2 is equal to 1, and so I can multiply that to the negative 3. Well, then I can use that law of logarithms to take this 3 that's being multiplied to the logarithm and rewrite it in the exponent. And that's how we get our next line. So now I have a logarithm base 2, subtract a logarithm base 2. If I'm subtracting logarithms, that means I'm subtracting exponents. That happens when I was dividing the powers. So since 2 cubed is equal to 8, this expression in blue is equal to log base 2 of 6 over 8, which I can reduce to log base 2 of 3/4. Let's try another example. Question number 10. We want to rewrite each expression in terms of log A, log B, or log C, or log C. So now we're working backwards. Instead of condensing everything to a single logarithm, we want to break it into its separate parts. So we're just using the logs in reverse, or the laws of logarithms. So here, because I'm dividing these two powers, that means I can subtract the exponents. Logarithms are exponents. And then we'll go one step further. Since I want a log b, not a log b squared, I can bring that 2 from the exponent down in front, and we get the log of a minus 2 times the log of b. Kind of looks like lag, but both of these are supposed to say logarithm. Well, question number 11. is for you to try. So why don't you pause the video at this point, work through question number 11, and then restart it to compare your answer with mine, and that will finish off this lesson. Well, here you can see my first step. Any parameter that was in the numerator or factor, the a squared and the b to the half, those end up being positive logarithms. And the parameter that was in the denominator, that gives me a negative logarithm. And then again, the exponents that are inside the logarithm, I can multiply out in front to get 2 log a plus 1 half log b minus log c. And again, we've separated out our expression so that we have a log a, and we have a log b, and we have a log c as the instructions we were given. All right, so hopefully at this point, you can explain how each logarithm law is related to an exponent law. So there are 3 laws. Hopefully you can make that explanation, and you can use them to simplify expressions. Not super challenging, it's useful. That would be the end of this lesson. So I'll see you again in the next lesson.